In this chapter, General Vector Spaces, we will define real vector spaces in its most general setting. In chapter 4, we defined Euclidean n spaces by adding more coordinate axes on 2 or 3 spaces. Here, we extract the most important properties of those Euclidean n spaces and turn them into axioms. And we will also define subspaces, which is a subspace is a vector space in itself, which is included in another vector space. We also introduce the concept of linear independence. A vector space is something with addition and scalar multiplication defined on it, and such that those two operations satisfy certain axioms. So let V be any non-empty set with two operations, addition and scalar multiplication. If certain axioms are satisfied for those two operations, then V is called a vector space. And the elements of vector space V is called, now those will be called vectors. And to become a vector space, there are 10 axioms. And for those, it's the list of those 10 axioms. You can read your textbook, page 222. And if you look at those axioms, the first 5 axioms about addition, and the next 5 axioms, the rest of it will be about scalar multiplication. So let's see, in particular, let's see 2 axioms. Say axiom 1. Axiom 1 is about addition. So if vector u and vector v are elements of those 2 elements, u and v are in vector space in V. So this is, at this point we do not know that it's a vector space or not. This is V is just a set, and u and v are 2 elements of V, a set V. Then this implies u plus v is also an element of V. So this is axiom 1. And there are 4 more axioms about addition. And now axiom 6. Axiom 6 is, if k is a real number, which we call scalar, and u is an element of V, then k times u is also an element of V. So, and there are 4 more axioms about scalar multiplication. So basically what this axiom says is that, so addition is well defined on this set, and scalar multiplication is well defined on this set. So this is minimum requirement for those 2 operations. And actually we choose a scalar in the real numbers R. So therefore these are called, if it satisfies these 10 axioms, they will be called real vector spaces. We can also choose scalars from the complex numbers. In that case, we will call them complex vector spaces. But in this course, we will just think about real vector spaces. Now let's take examples of vector spaces. And each examples are actually important. So first, Euclidean n space Rn is a vector space. This example will not be surprising to you because we already call them vector spaces. And most important properties, actually the most important properties of these vector spaces, Euclidean n spaces, are extracted and they become axioms to define general vector spaces. So now next we see a bit more unexpected, something unexpected example. Say, second example of vector space. The set of all 2 by 2 matrices is a vector space. So let's check some axioms. Let's say M2 be the set of 2 by 2 matrices. The set of all 2 by 2 matrices. Now let's choose 2 elements. Say U and V in M22. So U is an element of M22 means U is a 2 by 2 matrix. Say U can be written as U11, U12, U21, U22. Also, V is an element of M22. In other words, it is another 2 by 2 matrix. V11, V12, V21, V22. So let's add these two matrices, U plus V. Then we have usual addition on matrices. Therefore, this is U11 plus V11, U12 plus V12, U21 plus V21, U22 plus V22. In other words, the sum of these two elements in M22 are another 2 by 2 matrix. So, in other words, this is an element of M22 again. So, we could check this is axiom 1. So, this is the first axiom of those 10 axioms that define a vector space. So, now let's choose K a real number, then K times U. So, for K is a real number, and this is, we have usual scalar multiplication defined on matrices. So that's KU11, KU12, KU21, and KU22. As you can see, this is another 2 by 2 matrix. So this is axiom 6. And you can check all other axioms. The remaining 8 axioms can be easily checked so that this is a vector space, and in this vector space, these elements will be called vectors. More generally, we can say, let M and N be the set of all M by M matrices. Then this is a vector space. So we can use exactly the same argument as before, and we can get generalization. So this is a vector space. So we should specify the addition and scalar multiplication on this set. So with usual addition and scalar multiplication defined on it. Multiplication on matrices. Now we will see another example. Say, let F be the set of all real valued functions, then it will be another vector space, and we will see it on the next board.